Imagine this scenario, right? It's a Friday afternoon,
Oh, it's always a Friday.
always a Friday, and you have just updated this single, like seemingly completely harmless line of code in your machine learning model. You push the update, and
Yeah.
suddenly your entire customer-facing AI application just completely flatlines.
Just completely dies.
Right.
As
And
in,
you spend the next, I don't know, 4 hours frantically tracing the air, poring over the logs, only to find out that the model itself was actually perfectly fine. The code was pristine.
yep.
The failure was actually in the clunky duct tape pipeline that was trying to deploy it. You had, one tool for data processing, another one for training, and then a completely different, like, proprietary system for the live application.
Yeah.
And that single line of code just caused the brittle bridge between all of them to snap.
I mean, it is a total nightmare scenario, but the crazy part is it's incredibly common. We are living in this era where the design of the algorithms themselves has just skyrocketed in sophistication. But the infrastructure required to actually orchestrate those algorithms, like getting them to process data, train, and interact with live users without breaking, is frequently stuck in the dark ages. It's usually just a chaotic tangle of static scripts.
Which is exactly why today's deep dive is going to be so relevant for you, whether you're, say, an academic researcher running highly complex experiments or an engineer on a massive MLPops team at a global enterprise.
Absolutely.
We're exploring a stack of sources today that detail a genuinely game-changing framework. It's called the HumAIne Workflow Scheduler. And the mission today is to figure out how this specific open source platform is, breaking the mold of those rigid, easily shattered AI pipelines to create something that actually achieves seamless orchestration.
Yeah, and to really understand what HumAIne is doing, we sort of have to look at its underlying philosophy. It approaches this entire Friday afternoon disaster scenario through the lens of machine learning operations, or MLOps.
Yeah, right. MLO.
Because MLOps is basically the understanding that writing the algorithm is maybe, I don't know, 10% of the actual battle. The other 90% is managing the life cycle of that model. So to handle that, HumAIne is built directly on top of the Kubeflow toolkit.
Okay.
And Kubeflow is already this massive powerhouse for deploying machine learning workflows on Kubernetes. HumAIne leverages that to support literally everything from your initial coding and development phase all the way through deployment, and crucially, the ongoing monitoring of those models once they're actually in production.
But wait, hold on, because the term orchestration framework is thrown around in like almost every single tech pitch these days.
Oh, for sure. It's a huge buzzword.
Right. Everyone claims to organize the chaos.
Oh.
But looking at the documentation, it seems the major differentiator for HumAIne is its focus on open source modularity. Let's dig into that for a second. Why is modularity the actual silver bullet for the fragmentation you were just talking about?
Well, think about the current landscape of these tools. If you're building an AI workflow right now, you're dealing with massive fragmentation. You might use Kubeflow for the heavy lifting, training your models on a Kubernetes cluster.
Sure.
But then you need to connect that model to a hardware device or an online web service. So you use something like Node-RB, which is fantastic for wiring those things together. The problem is Kubeflow and Node-RED exist in complete isolation. They're just silos.
Oh, I see.
Yeah, HumAIne attacks that specific market gap by introducing what they call unified pattern-based orchestration.
So it's pulling these completely isolated, heavy-hitting tools into a single cohesive environment.
Precisely. And because that unified environment is open source, it fundamentally shifts how teams can interact with it. You're not locked into a proprietary ecosystem where some massive tech company dictates exactly how your pipeline has to be structured.
Right.
It lowers the barrier to entry significantly. You don't need a massive corporate budget to spin this up, which then fosters community-driven development. I mean, if a researcher finds a new way to optimize a data fetch, they can just contribute it back.
That makes a lot of sense. I always picture traditional closed-loop AI deployment tools like buying one of those pre-glued jigsaw puzzles.
Oh, that's a good way to look at it.
Right. Like you buy it, the picture looks amazing on the box, but you absolutely cannot change it. You are locked into the exact image the manufacturer gave you. If your business scales or your research suddenly pivots and you need to incorporate a new data stream, you basically have to throw the entire puzzle in the trash and buy a new one.
I like that analogy, but with open source modularity, this unified pattern-based orchestration we're analyzing, it's less like a puzzle and much more like standardizing a massive set of Lego blocks.
Okay, Lego blocks.
Yeah, because HumAIne provides the foundational base plate. But as your project scales, you aren't throwing anything away. You just swap out the pieces. You can build a highly rigid data crunching machine today and snap on a real-time user interface tomorrow, all on the exact same foundation.
And looking at who actually benefits from this Lego approach, the sources are highly specific. They point to academic researchers who are constantly iterating, MLOps teams at rapidly ramping businesses who need to scale without breaking their systems, and system integrators.
Oh, integrators have it the hardest.
They really do. Because they're building custom solutions for clients using wildly heterogeneous mixed bag AI tools. They desperately need those standardized connections so they don't have to custom code a bridge every single time they introduce a new tool to a client's stack.
Exactly, because that customization is where the friction of automation usually peaks. When you have to hard code the connections between entirely different phases of a machine learning lifecycle, you introduce fragility.
Okay, so I'm tracking with the Lego idea. But practically speaking, an AI workflow isn't just one type of task. You have incredibly rigid, predictable things like cleaning a data set. And then you have highly unpredictable things like a user randomly querying a chatbot.
Right.
How does HumAIne physically separate the rigid tasks from the flexible ones without just putting them back into isolated silos?
So that is the core architectural brilliance of the system. It divides the orchestration into a two-layered architecture. They recognize that trying to use one tool for both rigid and flexible tasks is like trying to use a hammer to drive a screw.
Right, wrong tool for the job.
Exactly. So the first layer is dedicated entirely to AI sequences. This handles the static sequential work, and it relies on a visual plugin based on Elira.
And just to clarify for the listener, Elira is an extension for Jupyter Notebooks, which is where a lot of data scientists are already writing their code anyway, right?
Yeah, it's a familiar environment, which is key for adoption. Elira provides this drag-and-drop interface right inside your Jupyter notebooks or Python scripts. You use this first layer to construct those sequential machine learning workflows. We're talking about the highly predictable step-by-step processes.
Okay.
You fetch your historical data, you clean and pre-process that data, and you run the training algorithm on it. Step A absolutely must finish before step B can even think about beginning.
That makes perfect sense for training a model. But as an engineer, if I hear two layers, my immediate thought is, great, more complexity.
Sure, yeah.
If Elira is handling the static sequence, what is the second layer doing? And what does the transition actually look like on my screen? Because I don't want to just be running a sequential script and hoping it eventually talks to the live application.
The transition is where the magic happens, and it's handled by the second level, event-driven integration. This layer is powered by Node-RED, which is an asynchronous platform. This is what generates the real-time interactive integration that completely separates HumAIne from older, purely static platforms.
Break down the actual mechanics of that for me. What is the functional difference in the real world between a static pipeline and an asynchronous one?
Well, think of a static Elira pipeline as essentially a recipe. You gather your ingredients, you mix them, you put them in the oven, and you bake. It runs from start to finish. If the oven breaks halfway through, the whole recipe fails. The static pipeline expects the entire world to pause and wait while it does its job.
Right.
But when you deploy a model into production, the real world does not wait. The real world is messy, it's unpredictable, and entirely asynchronous.
Yeah, users are clicking buttons, APIs are updating, data is streaming in at random intervals.
Exactly. So let's use a tangible example. Imagine your machine learning model is powering an AI customer service agent. The static Elira layer handles training that model on new support tickets every night at 2:00 a.m. That's a sequential, predictable recipe.
Right.
But at 2:00 p.m. the next day, hundreds of human users are sending messages to that agent at completely random intervals. An asynchronous Node-RED layer isn't running a start-to-finish recipe, it's standing by, just listening. When a user sends a single message, which the system registers as an event, Node-RED instantly catches that event, routes it to the trained model, gets the prediction, and routes the answer back to the user's messaging system. It does all of this in real time, without having to restart any overarching sequence.
Oh, wow. I see. So the transition for a developer is shifting from writing a script that just says, do this, then stop, to actually designing an environment that says, when this specific event happens, react like this immediately. It's moving from clunky batch processing to a living, responsive system.
Yes. You are building reflexes instead of just writing instructions. The static layer does the heavy lifting of training in the background, and the asynchronous layer provides the real-time reflexes for the live application. Having both coexist in one Unified visual drag and drop environment is a massive leap forward. You do not have to write custom glue code to bridge the 2.0 AM training pipeline and the 2.00 PM live application. The framework handles the handoff.
Okay, the handoff sounds seamless, but let's look at the reality of the scale here, because we're talking about massive multi-layered real-time interactions. You have live data flying in from users, you have Lyra spinning up heavy training models in the background, you have external APIs pinging the system, and remember our target beneficiaries,
Ah,
academic researchers, envelope ops teams, system integrators.
right.
You could easily have dozens of different people or completely different departments running their own two-layered architectures on the exact same overall system.
Mm.
How does this not devolve into absolute chaos?
That brings us down to the bedrock infrastructure. To secure all of this simultaneous activity, HumAIne relies heavily on Kubernetes. The framework is designed to allow the management of multiple distinct projects at the same time while maintaining strict, impenetrable isolation. In enterprise terms, this is multi-tenant security.
Okay, I want to push back on that term, multi-tenant security. It sounds great on a marketing slide to say everyone can share the same infrastructure safely, but is it actually safe?
It is, yeah.
Like, if my team is building a highly sensitive proprietary financial model and an academic team is running wild experimental workflows on the exact same physical server racks,
Yeah.
how does Kubernetes actually prevent them from crashing my model or, worse, seeing my data? Walk us through the physical mechanics of that separation.
It's a crucial concern. If we use the analogy of a massive high-security office building, Kubernetes doesn't just put different teams in different cubicles, it puts them in completely separate, sealed-off wings. The two mechanisms that act as the security detail are Kubernetes namespaces and RBAC role-based access control. Let's look at the mechanics of a namespace first. A namespace is essentially a virtual cluster carved out inside your physical cluster.
So it's a logical partition.
More than just logical, actually. It dictates resource allocation at the kernel level of the operating system. So the academic team is placed in namespace A, and your financial MLOps team is in namespace B. From the perspective of the software running in namespace A, namespace B literally does not exist.
Wow.
Yeah, they cannot see each other's processes, they cannot access each other's memory space, and they cannot accidentally consume each other's CPU limits if one of them writes a bad script that goes rogue. The namespace provides absolute environmental isolation.
That makes sense for separating the teams from each other. But what about separating individuals within the same team? Because isolation alone doesn't stop a junior developer on my financial team from accidentally deleting the production model.
And that is exactly where RBAC steps in. If the namespace is the sealed-off wing of the building, RBAC is the cryptographic keycard required to interact with anything inside that wing. It stands for role-based access control, and it defines the precise granular permissions for every single user or even automated service accounts within a namespace.
Just like the VIP list.
A highly specific VIP list. It dictates the verbs. Can this user view the pipeline? Can they execute it? Are they allowed to modify the code? By combining these two mechanisms, RBAC ensures that your junior developer might only have permission to monitor the workflow's health, while only the lead engineer has the authority to deploy a change.
On it.
So together, namespaces and RBAC create a multi-tenant environment where different teams and different roles within those teams work on the exact same underlying hardware with zero risk of cross-contamination.
Okay, so the invisible walls are up, the key cards are programmed. But how do we actually get the workflow into that secure room? The sources highlight that when a team is ready to execute, workflows are exported safely as YAML files.
Yes.
For anyone listening who isn't deep in the DevOps weeds, what is the practical value of a YAML file here? Why not just click a run button on the server?
Because clicking run on a live server usually means you're relying on whatever software happens to be installed on that server at that exact moment. It leads to the classic developer excuse, well, it worked on my machine.
Oh yeah, heard that a million times.
Right. A YAML file eliminates that completely. It's a configuration file, essentially a highly detailed plain text receipt. When you exploit your workflow from HumAIne, it generates this YAML file containing every single container definition, every dependency, and every library your code needs to run.
So instead of manually installing Python packages on a server and just praying they don't conflict with what is already there, you just hand the system this YAML receipt. It reads it, pulls the exact isolated containers it needs, and runs the workflow in a bubble.
Precisely. You upload that YAML directly to the user dashboard for execution. It guarantees standardization. Your workflow will run exactly the same way on the production cluster as it did on your local laptop, because the environment is defined in the file, not by the server.
right? The building is secure. The YAML files have defined the exact environment. But a secure, well-defined room doesn't mean the work is actually getting done. How does the system wake up and do its job without a human sitting there pressing buttons all day? Let's dive into the heartbeat of this entire operation: automation and scheduling.
Automation is the ultimate goal of MLOps. If you are babysitting your pipelines, you aren't doing MLOps. With HumAIne, executions can be programmatically triggered, actively monitored, or killed entirely via the Kubeflow Pipelines API. Think of that API as the master control switchboard for the entire Kubernetes cluster.
But the architecture deep dive reveals that the real magic, the actual brains behind the scheduling, happens back in that Node-RED environment. It relies on highly spatialized, time-based scheduling mechanisms.
Yes, within the asynchronous node-ready layer, there are specific workflow client nodes dedicated to managing time-driven events. There are two incredibly powerful nodes we need to dissect. The first is the recurring pipeline schedule node.
Break that down. What is it actually doing?
Its primary function is to set up a pipeline run and configure it as an automated recurring execution. You feed it parameters, start times, end times, and intervals. But the key here is that it can do this statically or dynamically.
I want to pause on that distinction because it is huge. If it was just static, you were essentially setting a dumb alarm clock, run the data ingestion pipeline every day at 5:00 p.m., regardless of what is happening.
Right.
But dynamic implies that the system itself can alter the schedule on the fly.
It adapts. A dynamic schedule means that based on external factors, say a sudden massive spike in user traffic, the system can automatically adjust the interval. It might say data volume has tripled. We need to change the training interval from every 24 hours to every 2 hours. And it does this without a human ever rewriting a line of code.
That is incredible. But a schedule is just a plan. How does the rest of the system know when the plan is actually happening?
That is the job of the second critical component, the recurring pipeline event listener node. They work in tandem. The event listener node acts as a continuous silent sentry. Its sole purpose is to wait for the exact millisecond a scheduled recurring execution begins and immediately output the unique pipeline run identifier.
Wait, I see how this connects.
Yeah,
Because traditionally, if you have a scheduled job running, the rest of your system has to constantly pull the server. It has to keep asking, is it done yet? Did it start yet? What is the status? Which eats up massive amounts of compute and creates latency.
polling is incredibly inefficient. It's like calling a restaurant every 5 minutes to ask if your table is ready.
Yes, exactly. But with this setup, the schedule node kicks off the process based on dynamic needs. And instead of the system tapping its foot and asking, are we there yet? The event listener node just waits quietly. The exact moment the execution fires, the listener catches the unique run ID.
Yep.
It instantly broadcasts to the rest of the system. Run number 45 is officially live, which means you can trigger the next phase of your workflow immediately based on that specific ID.
You eliminate the latency entirely. It is the transition from pulling information to having critical information pushed directly to you. By pairing a dynamic schedule that adapts to data volume with a continuous event listener that broadcasts exact identifiers, you completely bypass the brittleness of traditional manual triggers. You create a seamless, self-orchestrating loop where the system talks to itself perfectly.
So, synthesizing all of this for you, the listener, what does the HumAIne Workflow Scheduler actually represent? It seems to me that it systematically dismantles the massive obstacles that make AI automation such a headache.
It really does.
It replaces fragmented, siloed tools with a unified visual template. It provides a cohesive ecosystem where the highly predictable static ELIRA sequences live right alongside the asynchronous real-time reflexes of Node-RED. And it manages this complex dance while ensuring absolute kernel-level multi-tenant security on Kubernetes.
And it achieves all of this while remaining open source, modular, and highly scalable. It provides the foundation, but you hold the Lego blocks.
As we wrap up his deep dive, there's one specific phrase from the source material that really stands out to me. When listing who benefits from this architecture, the documentation specifically highlighted academic researchers who create human AI collaborative workflows.
The word collaborative is a very deliberate choice there.
Exactly. It doesn't say human AI tools or human AI scripts. It says collaborative workflows. And that is the final thought I want to leave you with today. We've spent this time exploring how tools like HumAIne make the orchestration of complex AI incredibly seamless and secure. But if the infrastructure truly becomes this invisible, if you no longer have to spend your Friday afternoons manually fixing broken deployment bridges or playing bouncer for your own server racks, How will your day-to-day role actually shift?
That's the real question.
Will the reduction in cognitive load finally allow you to stop being a mere pipeline builder, constantly maintaining the plumbing, and step into the role of a true collaborator, interacting with your AI systems as real-time peers?
When you remove the friction of just keeping the system alive, the nature of the work you can accomplish fundamentally evolves.
It's a massive shift in how we approach machine learning, and it really feels like we're just standing on the edge of what these unified systems can do. Thank you for joining us for this deep dive. Keep questioning the tools you use, keep building, and we will catch